For more problems and videos like this for linear algebra, you can take a look at Sarai Studies. Link is in the description box below. We're told to show that this set of vectors is an orthogonal basis for R3, so the third dimensional space of all the numbers, aka the 3D world. Let's first focus on the first part, which is to show that this set of vectors is an orthogonal basis. So let's define what this set of vectors actually is. Remember that a set is just a collection of vectors and it's surrounded with little squiggly lines. They're telling us that the first vector is u1. They're telling us that the second vector is u2, and that the third vector is u3. So they're asking us to show that this set of vectors is an orthogonal basis. Let's go step by step. First, we have to show that it's orthogonal. How do we know that a set is orthogonal? Well, that would mean that for every two vectors that I pick from that set, they should be orthogonal. And if I pick another vector and another vector, they should be orthogonal. So orthogonal means perpendicular, so they should all be perpendicular to each other no matter which I pick. So for every two vectors, we actually have to show that they're orthogonal. How do we do that mathematically? By using the inner product. The rule is if the inner product is equal to 0, then they're orthogonal. I'm going to check this one and this one. That's going to be 1, 0, -1, and then the other one is 1, -4, 1. So the inner product is just you multiplying the first term by the first term, so that's 1, and the second term by the second term, so that's 0, and the third term by the third term, so that's going to be -1. And 1 minus 1 is equal to 0. So yes, these two vectors are orthogonal because the inner product is equal to 0. But this has to be true for all of the two different vectors that I pick in this set. So I have to go through all of the possible pairs. So I did this one, and then I'm going to continue with this one and then do this one. So that's the blue vector with the green vector. Again, inner product is just multiply the first number by the first, so that's 4. Then plus 0 times 2, that's 0. Then plus -1 times 4, which is -4. 4 minus 4 is equal to 0. So yes, these two vectors are orthogonal because their inner product is equal to 0. Now, the last pair that we're left with is checking if these two are orthogonal. So I'm checking the pink and the green to see if their inner product is equal to 0. So again, first number times the first number, that's 4. Then -4 times 2, that's -8. Then the last one times the last one, that's +4. 4 plus 4 is 8, and then -8 is equal to 0. So yes, these two vectors are also orthogonal. So we just went through all of the possible pairs, two different vectors that we could pick from our set, and they're all orthogonal, meaning they're all perpendicular to each other because their inner product is equal to 0. So because all of these are orthogonal with each other, then we can say that this is an orthogonal set. But they're telling us to show that this is an orthogonal basis. So you think to yourself, well, what's a basis? A basis, specifically for R3, is a linearly independent set that spans R3. So it needs to be linearly independent. What does that mean? It means that all of these vectors, when you row reduce, the columns that have pivot, your pivot columns, are your linearly independent vectors. So those are the ones that you would leave as your bases. You can try row reducing, seeing which vectors are linearly independent, and then leaving those as your bases. Or you can use this beautiful theorem. The theorem says that if you have a set of vectors, in this case vector 1, 2, and 3, and it's orthogonal, then all of the vectors 1, 2, and 3, are linearly independent. So because I said that yes, it is an orthogonal set of vectors, if we know that we need to show that this set is a basis, and we know that in order for a set to be a basis, it has to be a linearly independent set, meaning that all of the vectors have to be linearly independent. If you have an orthogonal set, then it's automatically linearly independent. So therefore, this condition is satisfied, so now we can say that this is a basis. So we just showed not only is it an orthogonal set, but it's also a basis.